Okay, I'll do one last example of the divergence theorem, which recall was another way to do a flux integral, which is a surface integral. The divergence theorem can be applied when the surface completely encloses a solid volume. So in this case, here's the flux, or excuse me, here's the vector field, and here is the surface. It completely encloses the solid volume inside that sort of pyramid-looking thing. And remember the divergence theorem said this work integral becomes a triple integral where the integrand is the divergence of the vector field. What's the divergence going to be? Let's see. 2z plus 10y minus 2z. 2z's cancel, and you get a simple integrand again, just 10y. So our flux integral here now can be evaluated as a plain old triple integral, but we have to take that triple integral. Now here comes the hard part. Remember, the easy part is usually taking the divergence. The hard part is the triple integral. It's kind of a weird shape. You have to figure out, let's see, when x equals 0, well, the back side is just x equals 0. When x equals 0, z equals 2. So this is a 2 up here. Peaks up here for z, and z equals 2. And then down in the xy plane, z equals 0. To solve this, you get x equals 2. So x goes out to 2. And y will be 4. Those are the limits of the three variables, at least at their extremes. If you try to do, let's see, if you do any order where you do z before you do y, you would need to break it up into the two different surfaces. Z on this side here, z equals y. But over here, z equals 4 minus y squared. So of the 6 possible ways to order the variables of integration, we would like to not do z before we do y. And of these, here's the 6 permutations of those orders right here. We'll try to eliminate doing z before y. So we don't have to have two different, break up the integral. That leaves 3 different possible orders. XYZ, YXZ, or YZ dx. These are the 3 surviving permutations where we do y before z. And actually, we could do it any one of those. Any one of those 3 would work. Let's see, let's do XYZ. We do x first. X goes from the back side is 0. Front surface is this. We have to solve this for x, which will be the square root of 4 minus 2. Fortunately, it's all positive, so we don't need to worry about plus and minus on the square root. Then y. What does y do? Y goes from z on the left up to 4 minus z. And then finally, if we do z last, it just goes from 0 up to 2. Let's do this order. Let's do y first. Y will go from z to 4 minus z. Do x. X goes from 0 up to the same limits as before, square root of 4 minus 2. And then what does z do? Goes from 0 to 2 again. And finally, if we do dy, dz, dx, dy is the same, goes from z to 4 minus z. dz is now a little easier. doing x last, so we can just say z goes from 0 up to this here, which is 3 minus a half x. And finally, x, we said, goes from 0 to. So any of those three would work. I'll use this one because there's no square roots involved. I'm not going to go through that. So here's the setup. Here's the important part to get, including the limits. On my exams, I took off some serious points for getting the limit wrong. You can't just wave your hands about the limits. That's an important feature of getting the setup right. But you have to iterate those integrals. There was nothing super difficult to take the integrals. You just had to be careful with your book. But the lessons learned, taking the divergence is easy. Usually the easy part, the hard part is understanding the volume, getting the right order of integration, getting those limits set up right. That takes some time. Don't try to rush through that part. That's where the real meat of these problems is. So that ends EnMath A, and especially integral vector calculus. So just let me kind of review what we did in integral vector calculus. I only really covered two big things, the work integral and the flux integral. Work integral is a certain line integral. The flux integral is a certain surface integral. Here's their definitions. But we had multiple methods for doing that. The work integral, we could do it the normal way. If the vector field was conservative, we could use path independence. If the path were closed, we could use either Green's theorem or Stokes' theorem, depending on if it's 2D or 3D. Flux integrals, we could do it the normal way. I call it the normal way. But we had three different ways to do that. General method where you have to do some parameterization. But if the surface can be expressed as z is a function of x and y, use what I call the PQR formula. And actually, there's two more that could be done if you just want more formulas, where either of the three variables is a function of the other two. And finally, you can use the direct method when f dot n is a constant. Usually the hard part of that is knowing when f dot n is a constant. And if, other than the normal way, if your surface completely encloses a solid volume, use the divergence theorem we just talked about. You could put those in a decision matrix. Like when I gave exams, I didn't tell you which method to use. It boiled down to two big things. Is the vector, at least for the working, vector field conservative, and is the path closed? Both are yeses, then it's trivial. You get the answer of 0. If it is conservative but not closed, the best method is path independence. Covered what that is. The big X's mean the preferred method to use on my exams. Little x's mean it could work, but it's probably more effort. Dashes means it doesn't even apply. Not conservative, but it is closed, then you use Green or Stokes' theorem, depending on if it's 2D or 3D. If neither one is yes, it's not conservative and it's not closed, you're stuck with the normal method. Probably means the most. And about the flux integral, well, if it's closed, then use the divergence theorem. If it's not, do it the normal way, but we have 3 ways of that. Listed from easiest to hardest. Easiest is the direct method, where you don't even have to take an integral, but f dot n has to be a constant, and you need to know the area of the surface. On my exams, the big hint was that the surface was both flat and aligned with a with one of the ordinal planes, XY plane or YZ plane, one of those three planes. If you can get away with it, you'd like to do the direct method. If the surface is Z is a function of X and Y, then use PQR method. And if neither of those is true, here's your general method, which has several steps. And here's a little bit more explanation of parameterization when you use that general method. I don't know where the rest of these, the first two examples are, but first let's see. Find the flux of F through this given surface where this is the surface. I think I already did an example like this. C just goes between two limits, and X and Y are tied to each other. So you can solve for either X or Y in terms of the other. If I solve for X in terms of Y, I have parameterized this surface. It's just a function of X and Z. Did I see that right the other time? Excuse me, it's a function of Y and Z. X is parameterized in terms of Y, and Z is just off on its own. So the R becomes X, Y, Z, but X is in terms of Y here, and then Y and Z. So the two parameters are Y and Z. In every place there's an X in F, you replace it with what it is in terms of Y. Here's the new F, and here's the new R. Anyway, you might have to do some parameterization. That's it. That's it for EnMath A. That's it for integral vector calculus. And that's it for EnMath. So I'm all done with engineering math.